Usually when we think about how objects move in the physical world, we expect this, comforting precision.
Right, yeah, we really do.
Like you push a coffee mug across your desk and it just slides in a straight line.
Exactly.
You drop your keys, they fall straight down to the floor. You
God.
point your finger and nature says, there it is.
Yeah, it's linear.
Right, it's intuitive.
Yeah.
Up or down, left or right. It feels like the universe basically operates on simple arithmetic that we all mastered on the playground.
It is deeply comforting. I mean, we instinctively want the physical world to follow those visible common sense rules.
Definitely.
Our brains literally evolved to throw rocks and track gazelles, right? So we are wired for simple parabolic arcs and straight line intercepts. We crave that binary simplicity.
But the moment you look closer, like the moment you step into the world of complex dynamics, into high-frequency vibration, or into the realm of rapidly spinning masses, that simple arithmetic just shatters completely.
Oh, absolutely. It falls apart.
We're looking at a landscape of motion that is completely counterintuitive. It's a world where you push something forward and it violently twists to the side.
Right.
Or where an object seems to vibrate in place, but is actually hiding two perfectly mirrored ghosts racing past each other.
Yeah. It is the absolute definition of dynamic, murky waters, because in the real world, under the hood of advanced engineering, almost nothing is ever just moving in a straight line.
Never.
There are always hidden layers of rotation, vibration, and invisible forces pulling the strings.
And that is exactly what we are decoding today. We are taking a massive leap into the mathematical symphony that dictates the behavior of everything around us.
It's going to be a fun one.
From a child's toy spinning top, seemingly defying gravity, to a multi-billion-dollar space station struggling to stay pointed at Earth.
Yeah, or even the reason an explosion sounds like a sharp bang instead of a long roar.
Exactly. We are going to take the intensely abstract, blackboard-level math that engineers use to keep our modern world from shaking itself apart, and we're going to translate it into the physical phenomena you feel every single day.
But to even begin to understand those wild behaviors, we actually have to start with a lie.
Wait, a lie?
Yeah, a necessary foundational lie that engineers tell themselves just to make the math even remotely possible.
Okay, let's unpack this. You're talking about the concept of the rigid body, right?
I am, yeah.
Which, honestly, outside of a physics classroom, sounds vaguely like a forensic term. But structurally, it is the bedrock of dynamics.
It is. So in dynamics, a rigid body is a purely theoretical object. It has a finite volume, mass, and shape, but the absolute rule is that it cannot deform. Under any circumstance.
Zero deformation.
None. No matter how much force, torque, heat, or pressure you apply to it, the microscopic distance between any 2 points on that body remains exactly the same. It never bends, it never stretches, it never squishes.
Which is obviously impossible, right? I mean, even a solid block of titanium is going to flex or compress on a microscopic level if you hit it hard enough with a hammer.
Of course it is. But imagine you are trying to calculate the trajectory of an airplane flying through the sky.
Okay.
Or a steel gear spinning inside a car's transmission.
Right. Lots of moving parts.
Exactly. If you had to simultaneously calculate the macro movement of the object, like where it is actually going, while also calculating the microflexing of every single atom inside the wing or the gear teeth, the equations would instantly become unsolvable.
It's just too much data.
Way too much. The complexity would overwhelm any supercomputer. So by assuming the object is perfectly rigid, we isolate just its overall trajectory and rotation.
That makes sense.
It simplifies the math immensely without losing the practical accuracy we need to build machines.
And once we establish that perfect, unbreakable object, we arrive at this beautiful piece of mathematical logic called Chasles' theorem.
Oh, I love this one.
This was a massive aha moment for me in the reading. Because if you take a weirdly shaped object, let's say a heavy crescent wrench,
Okay, a wrench.
and you throw it end over end across the room, the way it tumbles through the air looks chaotic. It looks like an absolute nightmare to track mathematically.
It does look chaotic, yeah, because different parts of the wrench are tracing completely different paths through the air.
Right.
The heavy head of the wrench is doing these tight little loops, while the handle is sweeping out these massive erratic arcs.
But Chasles' theorem proves that it is essentially an optical illusion of complexity. No matter how wildly that wrench is tumbling, its entire movement can be mathematically broken down into just two incredibly simple components.
Straight line translation and rotation around a point.
Just slide and spin.
Exactly. That is the genius of it. You can take the most chaotic, tumbling, unpredictable trajectory imaginable, and mathematically, it is perfectly described by doing just two things.
Okay, walk me through it.
First, you find the object's center of mass, and you plot its path, which, for a thrown wrench, is just a perfectly smooth, simple parabola.
Oh, that's the slide.
Right. Second, you calculate how the rest of the wrench is rotating around that center point as it travels along the parabola. That's the spin. Chaos boiled down to just slide and spin.
It feels like a magic trick. You isolate the slide, you isolate the spin, and suddenly you own the motion.
You do.
But this illusion of simplicity only holds up if we, the observers, are standing perfectly still on solid ground. Where this gets genuinely mind-bending is when we change our perspective.
Oh boy. Yeah.
What happens when the ground beneath our feet is spinning?
This is the realm of moving frames of reference, and this is exactly where human intuition starts to aggressively fail us.
Aggressively fail is a good way to put it.
Because we are used to Newton's laws of motion. We are used to the idea that an object at rest stays at rest unless a physical force acts upon it.
Basic physics.
Right. But when you set up your coordinate system, your reality, on a platform that is itself accelerating or rotating, Newton's laws suddenly seem to break. Objects start accelerating without any physical hand pushing them.
Right. The math reveals these four distinct effective forces that just manifest out of nowhere. I want to walk through these conceptually because they explain so much of the physical world. Let's start with the most relatable one, the translational inertial force.
Okay, this one doesn't require rotation, just acceleration. Imagine you are sitting in the passenger seat of a car, holding a cup of coffee.
A dangerous game.
Definitely. The driver suddenly slams on the gas pedal. From your perspective inside the car, your frame of reference, you feel a violent force pushing you backward into the leather seat. The coffee sloshes backward.
But there is no physical entity pushing you.
None at all.
If I'm standing on the sidewalk watching you, I don't see a ghost pushing you backward. I see the car accelerating forward, and your body is simply trying to stay exactly where it was. The seat is actually pushing forward into your back.
Exactly. But because your brain is mapping reality from inside the accelerating car, the math requires a correction.
Right.
To make Newton's laws work inside that car, we have to invent an inertial force pushing you backward. It is the mathematical mirror image of the car's forward acceleration.
That makes total sense. We feel that every day. But the second one gets a little weirder, the angular acceleration inertial force.
For this one, imagine you place a heavy wooden box near the edge of a playground merry-go-round.
Okay, I can picture it.
You grab the bars and you suddenly heave on it, spinning the merry-go-round up as fast as you can. From the perspective of someone sitting in the center of the merry-go-round, the moment you accelerate that spin, the box suddenly wants to slide backward.
Opposite to the direction of the rotation, right?
Yes.
But again, it's just the box trying to stay still while the floor accelerates beneath it.
Right. But from inside that rotating frame, it feels like a very real force dragging that box backward.
So strange.
Now, the third force is the one everyone knows but often misunderstands: centrifugal force.
The classic outward push. If you swing a bucket of water in a big circle over your head, centrifugal force pins the water to the bottom of the bucket so you don't get wet.
Precisely.
The math involves the rotation interacting with itself and the distance from the center compounding to push the object away from the axis.
Yes, it's the force that drives outward from the center of rotation. But if we scale that concept up from a water bucket to the cosmos, it explains the fundamental reality of space travel.
I love this part.
People often look at astronauts floating inside the International Space Station and assume they are weightless because there is zero gravity in space.
Which is a complete myth.
Totally.
The space station is only about 250 miles above the Earth's surface. Earth's gravity up there is still roughly 90% as strong as it is on the surface.
Exactly.
If you built a stationary tower that high and stood on top of it, you would absolutely feel gravity. You wouldn't float at all.
You would fall right back to Earth very quickly. So why do astronauts float? Because the space station isn't stationary. It is moving sideways at over 17,000 miles per hour, orbiting the Earth.
Right.
It is in a massive rotating frame of reference. And because it is moving in a giant circle, it generates a massive centrifugal force pushing the station outward, away from the planet.
So they are perfectly trapped in a tug of war. Earth's gravity is screaming, pull down, pull down.
Right.
And the centrifugal force of their orbital speed is screaming, push out, push out.
Yes, and at exactly the right orbital velocity, those two extreme forces cancel each other out to zero. The astronauts aren't experiencing zero gravity, they are experiencing perfect, mathematically balanced freefall.
It is a phenomenal balancing act of forces.
Hmm.
But there is a fourth force that appears in a rotating frame, and it is by far the most elusive and strange.
The Coriolis
This
force.
is the one that really messes with your head. Let's go back to the merry-go-round. Imagine you and I are standing on opposite sides of a large, rapidly spinning merry-go-round. I have a baseball, and I try to throw it straight across the center directly into your hands. What actually happens?
So, from your perspective, looking straight at me, you throw the ball perfectly. But the moment it leaves your hand, it seems to magically curve away in midair.
It just veers off.
Yeah, it hooks sharply to the side, completely missing me. It looks exactly like an invisible ghost just swatted the ball mid-flight.
And that ghostly swat is the Coriolis force. It only affects objects that are already moving within a spinning frame of reference.
Right, it is the interaction of your throw's velocity with the spin of the floor beneath it.
Because while the ball is traveling straight across space, I am being carried away by the rotation of the merry-go-round, right? So I'm your target, but I moved.
Exactly. To you, spinning along with the ride, it looks like the ball curved. To an observer standing still on the playground grass, the ball traveled in a perfectly straight line, and you and I just spun out of its way.
But the wild thing is how this tiny playground physics scales up to control the fate of continents. The Earth itself is a giant rotating frame of reference.
It is.
And this Coriolis force is the driving factor behind massive global weather patterns.
It is the reason hurricanes rotate counterclockwise in the northern hemisphere.
Walk us through that.
Well, when the sun heats the ocean, the air rises, creating a massive zone of low pressure in the atmosphere. Naturally, the high-pressure air surrounding it wants to rush inward to fill that void.
Just like water rushing down a drain, it wants to travel in a straight line toward the center of the low pressure.
But as that air moves horizontally across thousands of miles of the Earth's surface, the Earth is spinning beneath it. Just like the baseball on the merry-go-round, the moving air experiences the Coriolis force.
Right, the SWAT.
Yeah. In the northern hemisphere, that force mathematically pushes moving objects to the right. So as the air rushes toward the center of the storm, it constantly gets deflected to the right.
So instead of flowing straight in and filling the void, the air spirals inward. It chases the center, constantly turning right, which creates that massive, terrifying, counterclockwise vortex that we see on satellite weather maps.
It really is amazing.
A mathematical artifact of geometry creates a storm that can level a city. But wait, I have to stop and ask a fundamental question here.
Sure.
I struggle with this concept. I remember learning in physics classes that centrifugal and Coriolis forces are literally called fictitious forces.
Yeah.
They're mathematically categorized as fake.
They are, yeah.
But if I'm on a merry-go-round and I feel pushed outward, my body is physically experiencing a force. If Coriolis can spin up a hurricane that rips the roof off a house, how can physicists call that fake?
What's fascinating here is that it comes down to a deeply philosophical definition of what is real in physics.
Okay.
When physicists say a force is real, they mean it originates from a fundamental physical interaction, like the electromagnetic pull of a magnet on iron or the gravitational pull of the Earth.
Something with a physical source.
Right. Centrifugal and Coriolis forces don't have a physical source. There is no magnet. There is no tractor beam. They are purely consequences of geometry and inertia.
So because they don't have a source, they get labeled fictitious?
Exactly. But, and this is the crucial distinction, if you are trapped inside that rotating frame of reference, if you are the astronaut in orbit, or the air molecule in a hurricane, or a person on a merry-go-round, those forces are as real as a punch to the gut.
They absolutely dictate your physical reality.
They do. Without these mathematical corrections, the entire framework of how reality operates from your perspective would collapse. They are the mathematical corrections required to make existence function in a rotating world.
The mathematical corrections of reality. I love that. So if spinning the ground beneath an object creates these bizarre invisible forces, what happens when we flip the script?
What do you mean?
What happens when we take a massive, rapidly spinning object and we lock it inside a rigid vehicle that is just trying to make a simple turn?
Oh, wow. That brings us into the wonderful, highly destructive, and often terrifying world of gyroscopic motion.
Let's explore gyroscopes. And we aren't talking about the little plastic ones you pull with a string. The engineering text sets up this incredibly visceral, high-stakes example of an early 20th century airplane.
Right, like a World War I fighter plane.
Exactly. Imagine a vintage fighter plane. Bolted to the front of this lightweight aircraft is a massive, heavy wooden and steel propeller.
A 30-kilogram propeller, to be precise, and it is spinning clockwise when viewed from the pilot seat at 2,000 revolutions per minute.
That is an immense amount of angular momentum. It is essentially a giant, lethal flywheel storing a terrifying amount of rotational energy.
It really is. Now, the pilot is flying straight and level, but they need to turn. They apply the rudder to make a flat, horizontal turn to the right.
Just a gentle sweep to the right.
Yeah, visually from above, the nose of the plane begins to pan across the horizon at, say, 0.2 radians per second.
And the moment that happens, the reality of the airplane completely fractures. What happens inside that engine?
The gyroscopic mathematics kick in with absolute brutality. The spinning propeller is a gyroscope, and the fundamental rule of a gyroscope is that it aggressively resists having its axis of rotation changed.
It wants to stay put.
It wants to keep pointing in the exact same direction in space. By forcing the nose of the airplane to turn right, the pilot is physically forcing the propeller's axis to tilt. They are applying a torque to the system.
And gyroscopes don't just resist torque, they retaliate.
Exactly. According to the mechanics of gyroscopic precession, the spinning mass responds to the pilot's turn by creating a massive reactive torque. But it doesn't push back against the rudder. It manifests exactly 90 degrees later in the direction of rotation.
It's the 90-degree shift that breaks the brain. You push the plane left or right, and the propeller reacts by violently pushing up or down.
Yes. The engineering analysis runs the numbers on this specific vintage plane, and by multiplying the massive inertia of the propeller by the speed of the spin and the rate of the turn, it calculates a gyroscopic moment that translates to nearly 7,000 newtons of force physically slamming onto the engine's shaft bearings.
7,000 newtons. That is roughly the weight of a small car suddenly dropped onto the engine block.
It's massive.
And it has a very specific direction. If the propeller is spinning clockwise, and you force the nose to turn right, the gyroscopic reaction mathematically forces the nose of the airplane to dive violently downward.
The pilot gently steps on the right rudder pedal, expecting to turn, and the airplane suddenly plunges toward the ground.
And if they panic and turn hard left to escape,
the 90-degree reaction flips. The nose violently pitches upward into a steep, stalling climb.
This wasn't just a math problem. This was a deadly reality for early aviators. They would enter a dogfight, bank into a sharp turn without anticipating the gyroscopic kick, and completely lose control of the aircraft. The engine was essentially fighting them.
The plane had a mind of its own, dictated purely by rotational inertia. Modern aircraft designers use counter-rotating engine spools, advanced flight control computers, and lighter materials to mitigate this effect. But the fundamental physics remains absolute.
If you turn a spinning mass, it will fight you on a completely different axis. But the beauty of engineering is that if a force is consistent enough to crash a plane, it is consistent enough to be harnessed.
That's true.
The exact same stubbornness that makes a propeller fight a turn is what allows us to navigate the globe. I want to talk about the earthbound gyrocompass.
Oh, this is truly one of the most elegant applications of dynamic math in human history. For centuries, ships navigated using magnetic compasses. But magnetic compasses are deeply flawed.
Very flawed.
They point to magnetic north, which wanders around the Canadian Arctic, constantly shifting. They are useless near the poles. And if you build a modern ship out of thousands of tons of steel, the local magnetic interference completely scrambles the needle.
So engineers needed a way to find true geographic north, the exact axis the Earth spins on without relying on magnetism. And they did it purely through math and rotation.
They did.
How does a mechanical box sitting deep inside the steel hull of a submarine know where true north is?
It knows because it literally feels the Earth rotating beneath it. We talked earlier about the Earth being a giant rotating frame of reference. The angular velocity of the Earth is tiny.
Right.
It completes one rotation every 24 hours. Mathematically, that is roughly 7.2 times 10 to the negative 5th radians per second. It is a crawl.
You definitely can't feel it standing on the street.
We can't feel it, no. But a highly tuned gyroscope can. A gyrocompass uses a spinning rotor suspended inside a series of gimbals.
Rings that allow it to tilt freely.
Exactly. But the engineers add a trick. They restrict its movement in a very specific way using springs or gravity pendulums. They force the gyroscope to stay relatively horizontal to the Earth's surface.
Okay, so because of that restriction, as the Earth slowly rotates beneath it, the spinning gyroscope feels a twisting force. It feels the planet trying to change its axis.
And just like the airplane propeller, the gyroscope resists. It wants to minimize the twisting forces on its gimbals. The math dictates that the only way for the gyroscope to stop feeling the torque of the planet's rotation is to perfectly align its own spinning axis with the spinning axis of the Earth.
Wow.
It seeks the path of absolute least mathematical resistance.
It is drawn to true north not by magnetism, but by geometry. It is essentially saying, if I spin in the exact same direction the planet is spinning, the twisting stops.
Exactly, but because it has mass and momentum, it doesn't just snap to north and stop.
Right, it has momentum.
It slowly turns toward north, builds up speed, and overshoots it. Then it feels the twisting force from the other side, slows down, reverses, and swings back. It tries to settle swinging past north, getting pulled back, swinging past it again.
It draws a slow, invisible pendulum swing back and forth across true north. And the math used to calculate how fast it swings is just breathtakingly beautiful.
It really is.
The equation links the moment of inertia of the spinning rotor inside the box, the exact rotational speed of the planet, the spinning speed of the gyro, and the cosine of the ship's exact latitude on the globe.
That equation is poetry. It directly links a cosmic variable, the rotation of an entire celestial body, to the localized mechanical wobble of a metal wheel sitting on a table.
By plugging in the variables for a standard navigational gyro, the math reveals that it will oscillate back and forth across true north with a very slow, highly predictable cycle.
Usually about 3.8 seconds per cycle for a standard rate gyro.
You observe that wobble, you calculate the exact center point of the swing, and you have found true geographic north. You have locked onto the fundamental rotation of the planet itself.
It is the perfect example of extracting absolute certainty out of complex, interacting motions.
So we've seen what happens when these rotational forces are bolted firmly inside an airplane or trapped inside a ship's navigational box. But what happens when the spinning object is totally free-floating?
Free-floating gyroscopes.
Right. What happens when it isn't trapped in gimbals, but is just resting on a point? Let's talk about the heavy symmetrical top, the classic toy.
It is the purest visual representation of this math. To explain how a top moves, engineers have to step away from simply calculating forces. They use an approach called the Lagrangian function.
The Lagrangian function.
Yeah. Instead of just adding up vectors, the Lagrangian looks at the entire energy state of the system, specifically tracking the kinetic energy of its motion minus the potential energy of its position in gravity.
When you spin a heavy top on a table, it leans over slightly. Gravity is pulling down on its center of mass, desperately trying to topple it over onto the table.
But the top's immense spin momentum fights back. Gravity pulls down, the spin reacts at 90 degrees, and the result is a compromise. The top doesn't fall. Instead, its tilted axis begins to draw a slow, sweeping circle in the air around the vertical point.
That sweeping circle is called precession.
Precession, exactly.
It looks like it is defying gravity. But if you watch a heavy top incredibly closely, as the friction of the table starts to slow its spin, it isn't just making a smooth, perfect cone.
Right.
The angle of its tilt is constantly bobbing up and down as it circles.
That secondary bobbing motion is called nutation. It is a subtle, vertical flutter superimposed on top of the slow precessional circle. It is caused by the constant microscopic tug-of-war between the top's rotational energy and the gravitational pull trying to pull it down.
And the math behind that nutation reveals something visually stunning. Depending entirely on the exact amount of energy you give the top when you first spin it, the equations dictate that the top will lock into one of three very distinct nutation paths.
Yeah, the first path is the most common. It creates smooth, rolling waves. As the top slowly circles, the axis just bobs gently up and down, tracing a weighty line in the air.
Like a gentle roller coaster.
Right. But the second path is where the math gets sharp. Literally, it creates what are called cusps.
Cusps.
This happens when the mathematics of the top's spin perfectly match the energy of the gravitational pull at the exact peak of the vertical bob.
What does that look like?
When it hits a cusp, the forward sweeping motion of the top, the precession, comes to a complete instantaneous halt at the absolute peak of its vertical bob. The axis traces a sharp point in midair, stops completely for a fraction of a millisecond before dropping back down and accelerating forward again.
It halts in midair.
Yeah.
But the third path is even stranger. If you spin it with a very specific lower energy ratio, the math forces the top to do loops.
Loops, yes.
The top bobs upward, slows down, and actually travels backward against its own precessional circle for a brief moment. It draws tiny retrograde loop-the-loops in the air before continuing on its forward path.
Smooth waves, sharp static cusps, or backward loops. When a child spins a wooden top on the kitchen floor, that toy is instantly executing higher-order calculus, solving differential equations in real time through its physical motion.
It's incredible. But what happens when we take that exact same physics, take away the kitchen floor, and scale it up to a multi-billion-dollar machine floating in a vacuum? Here's where it gets really interesting. Let's talk about spacecraft dynamics.
The rules of the toy top are the exact same rules that govern satellites. When you launch a massive satellite into a circular orbit around the Earth, it is incredibly easy to imagine it just floating there peacefully, suspended in the silent void.
But the dynamic environment of low Earth orbit is brutally complex.
It is a tempest of invisible forces. First, you have gravity gradients. A satellite, especially something like the International Space Station, is enormous. It spans hundreds of feet.
Right.
Because gravity weakens with distance, the bottom of the space station, the part closest to Earth, actually experiences slightly more gravitational pull than the top of the solar panels.
Gravity is constantly trying to twist the entire station, pulling the heavy parts downward.
Exactly. Then, because the station is moving in a massive circular orbit at 17,000 miles per hour, it is subjected to centrifugal force across its entire sprawling body. And, as we established in the very beginning, moving anything within a rotating orbital frame generates those ghostly Coriolis forces.
Because the satellite isn't a perfect, infinitely small dot, because it has mass distributed out on long booms and panels, different parts of the structure feel all these forces slightly differently. And this introduces the ultimate nightmare for guidance engineers, cross-coupled torques.
Let's visualize this. Say a small meteorite strikes the station, or an astronaut pushes off a wall, causing the station to roll very slightly to the left, just a tiny rotational drift.
You would think you just fire a tiny thruster to roll it back right.
You would think so. But as the station rolls, the heavy masses of its solar panels physically move through the orbital frame of reference. Instantly, the Coriolis and centrifugal forces grab onto those moving panels.
Oh, wow.
The math of the moving frame interacts with the physical roll, and it spontaneously generates a secondary, entirely new torque. Suddenly, the station isn't just rolling left, it starts to yaw, twisting horizontally off course.
You pitch up, and physics forces you to twist sideways. You try to fix the twist, and physics forces you to roll. The motions are irrevocably chained together.
They are.
Space stations don't just sit peacefully. The mere act of rotating a spacecraft, or even just letting it orbit, generates self-disturbing forces on all three axes simultaneously.
It is a cascading failure of stability, which is why you can't just point a telescope at a star and turn off the engines. Satellites require incredibly active control systems. They use massive internal gyroscopes called reaction wheels.
Fighting fire with fire.
Exactly. These wheels spin up and slow down, purposely generating their own gyroscopic torques to perfectly counter the cross-coupled torques of the orbit.
They are constantly fighting the invisible math of precession and nutation, just to keep the antenna pointed at our planet. It is a silent, unending war against the laws of motion.
Up until this exact moment in our exploration, we have been living in a theoretical paradise. We've assumed the airplane propeller, the child's top, the sprawling space station, we've assumed they are all perfectly rigid bodies. We pretended they don't bend.
But reality ruins everything.
It does. In the physical world, steel bends, aluminum stretches, carbon fiber flexes. There is no such thing as a perfectly rigid solid.
Sadly.
And the moment we acknowledge that undeniable fact, we have to abandon the relatively clean, predictable math of rigid body dynamics. We have to enter the terrifyingly complex realm of multi-degree of freedom system.
So you have to deal with vibrations.
Mm.
Let's ground this in something everyone has experienced. Let's look at the vibrating automobile.
Good example.
Imagine an ordinary car driving down a slightly bumpy road. If we simplify it to its most basic components, a car is a large mass, the body and engine, supported by two main springs, the front and rear suspension.
In engineering terms, this basic car is a two-degree of freedom system. It can move in two distinct ways.
Right.
First, it has vertical displacement. The entire car can bounce straight up and down on both springs equally. Second, it has angular displacement. The car can pitch forward and backward, diving on the front springs while lifting on the back like a rocking chair. Bounce and pitch.
Now, human intuition says, if I hit a speed bump with all four tires at the exact same time, the car should bounce perfectly straight up.
Right.
But the physics of a multi-degree system says that is almost impossible. The bounce and the pitch are statically coupled.
They are inextricably linked. Why? Because the center of mass of a car is almost never perfectly in the dead center between the wheels. The engine in the front is incredibly heavy. Plus, the front springs and the rear springs are almost never the exact same stiffness.
So if you have a massive weight in the front and stiffer springs in the back, and you try to push the entire car straight down toward the ground and let go, what happens?
The uneven forces from the mismatched springs and the off-center weight will instantly force the car to pitch forward or backward as it rises. You cannot have a pure vertical bounce. The math physically prevents it.
The energy bleeds from the bounce into the pitch and back again.
Yes, the motions are hopelessly intertwined.
So if everything is tangled together, how do automotive engineers ever solve for the motion of a car hitting a pothole? They can't just guess.
They turn to matrix algebra. Engineers set up two massive grids of numbers. The first is a mass matrix, which maps out exactly how the weight is distributed across the vehicle. The second is a stiffness matrix, which maps out exactly how much pushback every single spring and bushing provides.
Okay, so two big grids of data.
They take these two massive grids and multiply them together.
And when you crank through that complex matrix math, it spits out these magical, profound numbers called eigenvalues.
Eigenvalues are essentially the mathematical DNA of the structure. They are the natural frequencies of the car. Every physical object has them.
Right.
The engineering text gives an example of a specific car design where the matrix math dictates two distinct natural frequencies. One eigenvalue lands at roughly 6.9 radians per second. The second one lands at 9.1 radians per second.
Those are the frequencies where the car basically wants to vibrate. And paired perfectly with those eigenvalues are eigenvectors.
If the eigenvalue is the frequency, the eigenvector is the choreography. It is called a mode shape. It tells engineers exactly what physical contortions the car's body will undergo when it is stimulated at that specific frequency.
So at 6.9 radians per second, the eigenvector might dictate that the car will primarily bounce heavily up and down with just a tiny flutter of pitch.
Exactly.
But at the higher frequency, at 9.1 radians per second, the eigenvector might reveal a completely different shape. The car might wildly pitch back and forth, slamming the front bumper toward the ground with almost zero vertical bounce.
And this isn't just theoretical. This determines if a car is safe to drive. Imagine you take this specific car and you drive it down a dirt road that has been worn into a washboard pattern of rhythmic ridges.
Oh, I've driven on those.
If you drive at exactly the speed where your tires hit those dirt ridges at 9.1 times a second,
You hit resonance. The rhythmic energy coming up from the road perfectly matches the natural frequency of the car's most violent pitch mode.
exactly. The suspension can't absorb the energy fast enough. The car will absorb the impacts, perfectly match the road's rhythm, and amplify that rocking motion until the suspension violently bottoms out, the tires leave the dirt, and you completely lose steering control.
It's the exact same amplifying math that caused the famous Tacoma Narrows Bridge to twist itself to pieces in the wind.
Same exact concept.
But a car is relatively simple. Two springs. 2 degrees of freedom. How in the world do engineers solve vibration systems for a modern commercial jetliner or a skyscraper, which have literally millions of interconnected bending parts? You can't calculate a million eigenvalues simultaneously.
You really can't. The complexity would break even modern supercomputers. So engineers developed a brilliant shortcut called lumped parameters and transfer matrices. Instead of trying to write one infinitely massive equation for a continuous sweeping airplane wing, they slice the problem into pieces.
They metaphorically chop the wing up into chunks.
Yes. They treat the continuous, elegantly curved aluminum wing as if it were a series of heavy, rigid, blocky chunks, lumped masses. And they imagine these heavy blocks are connected to each other by massless, infinitely thin, flexible springs.
It's a fantastic visual. It's like taking a solid steel rod and mathematically turning it into a pearl necklace, a series of heavy beads connected by a flexible string. And for each individual pearl on that necklace, they define what is called a state vector.
The state vector is like a passport for that specific chunk of the wing. It documents exactly what is happening at that exact spot at any given millisecond.
What's in the passport?
It tracks 4 crucial things: the physical displacement, like how far it has moved, the slope, how much it is bent, the shear force, the tearing stress inside the metal, and the bending moment, the twisting torque.
So you have a passport of stress for chunk number 1 at the root of the wing, but how do you figure out what chunk number 2 is feeling?
That is where the transfer matrix comes in. It is a mathematical translation tool. You take the state vector passport from the first chunk, multiply it by the transfer matrix, and the math automatically translates how the spring between them will react. It instantly spits out the exact state vector for the second chunk.
You find the stress on chunk 2, then you multiply that by the next matrix, and you find the stress on chunk 3. You literally leapfrog your way down the entire structure.
You matrix multiply your way from the heavy root of the airplane wing, chunk by chunk, all the way out to the delicate wingtip. By doing this, engineers can digitally simulate a massive blast of turbulence hitting the wingtip and mathematically watch exactly how those violent vibrations travel down the pearls of the wing.
They can track the energy wave moving inward and pinpoint the exact rivet, the exact joint that will experience the most shear force. They find the invisible weak points in complex structures without ever having to physically build them and snap them in half.
It is an incredibly powerful computational method that basically built the modern aerospace industry. But, and this is crucial, it is still an approximation. You are taking a continuous, smooth reality and hacking it into discrete chunks.
Which is the perfect bridge into our next layer of complexity.
Yeah.
Because lumped masses are fantastic for skyscrapers and airplane wings. But what about a simple acoustic guitar string?
Right, a continuous system.
Yeah, a vibrating string doesn't have 2 chunks or 10 chunks or even 100 chunks. It is a continuous ribbon of matter. It has an infinite number of microscopic points that can move and vibrate simultaneously.
When you enter the realm of truly continuous systems with infinite degrees of freedom, the matrix grids aren't enough anymore. You have to step up the mathematical heavy artillery. You have to use partial differential equations. To explain how a guitar string vibrates, engineers rely on the one-dimensional wave equation.
When you pluck a guitar string, you pull it into a sharp triangle shape, and then you let go. To figure out exactly what shape that string will take as it rapidly vibrates over time, mathematicians use a technique called the separation of variables, combined with a Fourier sine series.
Fourier analysis is one of the most profound tools in all of science. It is the realization that any complex, messy, jagged shape, like a string pulled into a sharp point, can be mathematically broken down into an infinite stack of perfectly smooth, simple sine waves.
Wow.
It's like taking a complex, messy cake and mathematically unbaking it back into pure flour, sugar, and eggs.
You break the complex vibration down into a recipe of perfect waves. But here is the massive aha moment in the math. When you grind through the heavy partial differential equations for that plucked string, the incredibly complex math suddenly collapses. It naturally simplifies into a stunningly elegant result. The solution separates entirely into 2 distinct halves.
It splits into 2 independent functions. The equation becomes a function of x minus a times t plus a function of x plus a times t.
Okay, what does that actually mean in the physical world?
Physically, it is a revelation. It means that the complex, messy shape of the plucked string you see with your eyes is actually an illusion. The vibration is actually 2 perfectly identical waves. The x minus a times t function represents a wave sliding rapidly to the right. The x plus a times t function represents a mirrored wave sliding rapidly to the left.
Wait, really? So when you look at a guitar string humming, and it looks like a blurry blur of metal just vibrating up and down in place, what physicists call a standing wave, it isn't actually moving up and down. The string is hosting 2 ghost waves racing in opposite directions.
Exactly. The 2 waves are constantly rushing past each other, hitting the heavy wooden bridge and the tuning pegs at the ends of the guitar, bouncing off and passing through each other again and again.
That's wild.
The standing wave you see with your eye is just the visual interference pattern of those 2 traveling waves constantly overlapping.
The string isn't bouncing. It is a highway for 2 opposing waves of energy. It's a profound truth about how energy moves through a continuous medium. But a string is one-dimensional. The math only has to track energy moving left and right. What happens when we add another dimension? The engineering text shifts from guitar strings to drumheads, 2-dimensional circular membranes.
A drumhead fundamentally changes the geometry. When you strike the center of a snare drum with a stick, the vibration doesn't just travel left and right along a single line. It ripples outward in a continuous 360-degree circle, exactly like dropping a heavy pebble into a perfectly still pond.
And because that circular wave is spreading out over a larger and larger surface area as it moves toward the rim of the drum, the energy of the initial strike gets stretched. It gets diluted.
Because of that radial decay, the standard perfect sine and cosine waves from the guitar string won't work anymore. The math has to account for the wave losing its amplitude as it spreads. So the equations require a different mathematical tool entirely, Bessel functions.
Specifically, the text highlights the J0 Bessel function. If you look at it on a graph, it looks like a traditional undulating sine wave, but the peaks get lower and lower and lower as you move further away from the center axis. It is the mathematical fingerprint of a fading ripple.
It perfectly describes how energy dissipates across a 2D surface.
But I want to take this one dimension further. We went from a 1D string to a 2D drumhead. Let's move into full 3D space. How does this mathematical expansion apply to sound traveling through the air around us?
Sound is fundamentally just a pressure wave propagating through a fluid medium, whether that is air or ocean water. And the engineering text uses a fantastic, vivid analogy to explain this, the explosion of a firework.
Imagine a massive mortar firework exploding high in the night sky. It isn't a flat ripple. It is a spherically symmetric wave.
When the gunpowder detonates, it rapidly expands and radically compresses the air immediately surrounding it. That localized zone of extreme density, the high pressure, has to go somewhere. So it propagates outward in every single direction simultaneously. It forms a thin, rapidly expanding spherical shell of compressed air moving at the speed of sound.
The text points out that the actual physical thickness of this invisible shell is defined entirely by the size of the initial explosion. A small firecracker makes a very thin shell. A massive bomb makes a thicker shell. And as this sphere of pressure expands outward over a city, the amplitude of the waves, how incredibly loud it is, drops inversely with the radius of the sphere.
Just like the drumhead, but in 3 dimensions. The energy is being stretched over an infinitely larger surface area the further it travels. The shell gets thinner, and the sound gets quieter.
But the most fascinating physical insight is what is happening inside and outside that expanding bubble of pressure.
The math proves that the sound wave only exists inside the physical boundary of that expanding shell. Think about the air in front of the expanding sphere. It is completely undisturbed. It hasn't felt the pressure yet. It is in absolute silence.
And the air behind the shell, closer to the center of the explosion.
The high-pressure shell has already passed through it. The air has violently snapped back to its normal resting atmospheric pressure. It is also completely silent.
The blast only exists in the skin of the bubble. This is exactly why an explosion sounds like a sharp, concussive bang rather than a prolonged, rumbling roar.
Yes.
The sound literally vanishes from your reality the millisecond that incredibly thin shell of high pressure passes over your eardrum. It is a fiercely localized disturbance traveling through a continuous medium.
It is a stunning realization. If the 3D wave mathematics worked differently, if the wave didn't perfectly clear out the space behind it as it expanded, every single explosion, every hand clap, would leave a ringing, chaotic echo in the air for minutes.
That would be awful.
Our auditory world would be an unintelligible blur of overlapping noise.
We survive because the math of the spherical wave demands silence in its wake. Okay, we have covered immense ground, but we are entering the final and perhaps most dangerous conceptual realm.
The chaotic realm.
Exactly. Up until this moment, whether we were analyzing vibrating car suspensions, humming guitar strings, or exploding fireworks, we have lived entirely in a linear world. We have relied on a comforting assumption, proportionality. We assume that if you pull a spring twice as hard, it stretches exactly twice as far. You hit a drum twice as hard, the wave is twice as tall.
But the physical world has absolute limits. Matter can only endure so much stress. What happens when the vibrations get so violent or the rotational forces get so extreme that those simple, predictable rules of proportionality shatter?
Things break.
A spring eventually stops stretching linearly and starts permanently deforming. A pendulum pushed too hard stops swinging like a gentle sine wave and starts tumbling.
When proportion dies, we enter the realm of nonlinear vibrations. We enter chaos.
The engineering texts introduce the terror of nonlinear dynamics with a very real industrial nightmare scenario, the whirling of a rotating shaft. Imagine you are in a power plant and there is a massive, solid steel shaft, perhaps 10 feet long and thick as a tree trunk, spinning at incredible speeds. Mounted to the center of this heavy shaft is a large steel disc, like a turbine rotor.
But manufacturing is never perfect. The disc is just slightly unbalanced. Maybe it is heavier by a fraction of an ounce on one side.
Because of that microscopic unbalance, as the giant motor spins the shaft up to speed, centrifugal force takes over. The heavy side of the disc is pulled violently away from the center axis of rotation. The force is so immense that the solid steel shaft actually begins to physically bow outward in the middle, swinging around like a massive jump rope. This phenomenon is called whirling.
And it creates a devastating nonlinear feedback loop. The faster the shaft spins, the more the centrifugal force pulls the unbalanced weight outward.
Right.
The more it pulls outward, the further the solid steel bows. But the further it bows, the stronger the centrifugal force becomes because the mass is now further from the center.
It feeds on itself. It is an exponential runaway reaction. If left unchecked, the shaft will bow so far that it will either violently shatter its steel bearings or literally tear the entire machine out of its concrete foundation.
Now, every machine in existence has a resonance frequency, a specific RPM danger zone where this exact whirling effect is violently amplified by the natural flexibility of the steel. The ultimate goal of the plant operator is to get the machine spinning at its normal operating speed, which is usually designed to be safely above this dangerous resonance zone.
You have to spin up through the danger zone to reach the safety of high-speed stability.
Which leads to a highly counterintuitive engineering problem. Does the speed at which you accelerate the machine matter? If you are the operator standing at the control panel, turning on this massive turbine, should you throttle it up slowly and carefully to monitor the vibration? Or should you slam the throttle to maximum power?
The answer is entirely dependent on one hidden variable, the damping in the system.
Damping.
Yeah. Damping is how much friction or thick fluid resistance is present in the bearings to naturally absorb and bleed off vibrational energy.
And the mathematical findings are completely backwards to human intuition. Let's say the system has very little damping. It's a clean, low-friction setup. What do you do?
If there is low friction, the math unequivocally shows that you want to accelerate the massive machine as aggressively as possible. You slam the throttle wide open.
Which sounds insane. You have a vibrating jump rope of death, and you floor it.
You do it because the whirling amplitude takes time to physically build up. By accelerating with massive torque, you force the machine's RPM to tear through its natural resonance frequency so fast that the bowing simply doesn't have time to exponentially grow out of control.
Oh, I see.
You sprint across the minefield before the mines can detonate.
You outrun the resonance.
Yeah.
But if the system is highly damped, let's say the bearings are packed with incredibly thick, viscous oil that provides massive friction, the physics completely reverses.
Yes. In a highly damped system, if you slam the throttle, the massive inertial forces of rapid acceleration will completely overpower the damping fluid's ability to absorb the energy. The jump rope effect will spike instantly. So in a system with high friction, you actually want to accelerate it as slowly and gently as humanly possible.
You tiptoe through the minefield.
Exactly. You creep up the RPMs, giving the thick oil plenty of time to constantly bleed off the centrifugal forces, keeping the bowing manageable as you slowly pass through the resonance frequency.
It's brilliant. The exact opposite operational solution to the exact same physical problem, dictated entirely by the hidden nonlinear math of friction. Finally, to truly understand how close we always are to the edge of this chaos, the source material introduces an incredible visual tool. It's called the phase plane.
The phase plane is a powerful graphing technique that abandons time. Normally, when we graph motion, we plot position on the x-axis against time on the y-axis. The line moves left to right as the clock ticks.
Right, a standard timeline.
But on a phase plane, time is invisible. Instead, you plot the object's physical position on the x-axis, and you plot its velocity at speed on the y-axis.
You graph where it is against how fast it is going. Let's ground this. Let's use a simple, classic swinging pendulum, a heavy brass weight on a string. You pull the pendulum back a few inches and let it go. It swings back and forth.
If you trace that motion on a phase plane graph, tracking its position and its speed simultaneously at every millisecond, the pen draws a perfect closed circle on the paper, or an oval, depending on the scale.
It draws a trajectory. And the crucial detail is that the circle is closed. Because the line perfectly loops back onto itself, it mathematically proves the motion is repeating. The system is stable.
Yes.
It has a small, finite amount of energy, and barring air resistance, it will trace that exact same closed circle forever.
It is trapped in a stable loop. But what if you intervene? What if you grab the pendulum and push it much harder? You add more kinetic energy to the system.
On the phase plane graph, the circle instantly gets bigger. It swings further out in position, and it reaches a higher velocity at the bottom. You push it even harder, the circle gets massive. You are approaching the physical limit of the pendulum swing. It is swinging so high, it is almost going horizontal.
And this is where the phase plane reveals its genius. The math identifies an exact, infinitely thin boundary line on the graph. This line represents the exact amount of energy required to push the pendulum straight up so that it balances perfectly upside down at the absolute top of its arc.
That critical boundary line on the graph is called a separatrix. It is the mathematical wall that separates two entirely different realities of physics.
Inside the separatrix, the pendulum swings back and forth. Gravity always wins. The energy is contained. The motion is defined by stable, closed circles.
But the very moment you add just a fraction of an ounce more energy, the moment you cross the separatrix, the pendulum goes over the top, it stops swinging back and forth, and it starts doing continuous 360-degree loops around the pivot.
On the phase plane graph, the visual is striking. The closed, stable circles violently break open, the trajectory line snaps, and it becomes a wavy, continuous river that snakes infinitely across the page, never looping back on itself.
Wow.
This open line represents rotary, unstable, tumbling motion.
The separatrix is the absolute tipping point. It is where predictable, contained oscillation violently shifts into unpredictable, uncontained chaos. And along this boundary, the math defines points of extreme focus called singular points.
The dead bottom of the pendulum swing, when it is hanging straight down, perfectly still, is called a center. Mathematically, it is the ultimate point of stability. All the closed circles of energy orbit around it. If you bump it, it just wants to settle back to the center.
But the exact top of the arc, that precarious point where the pendulum is balanced perfectly upside down, is called a saddle point.
Mathematically, a saddle point is the definition of absolute instability. If a pendulum is balanced perfectly on a saddle point, the slightest change in the universe, a microscopic breeze, the vibration of a footstep, a fraction of a degree of temperature change will break the balance.
It's teetering on the edge.
It is. It will send the pendulum either falling backward into the stable, swinging circles, or tumbling forward over the cliff into chaotic rotary loops. You can never predict which way it will fall.
So we spent all this time deep in the weeds of engineering textbooks, tracking vectors and eigenvalues. But what does this all mean for us, the people not building airplanes or writing orbital algorithms? Why should we care about the phase plane of a pendulum?
Because the mathematics of stability scale up to every complex system we interact with. Stability isn't just a question of whether a titanium wing flexes or if a concrete bridge stands under a heavy load. It is about recognizing that every dynamic system has invisible thresholds. Systems that seem perfectly predictable and incredibly robust can suddenly become wildly, irreversibly unpredictable. And it doesn't happen because the fundamental rules of reality change. It happens because we push the system across a hidden separatrix.
We've covered an unbelievable amount of ground today. We started by breaking the illusion of simple motion. We explored the fictitious, ghostly forces that govern our rotating world, the Coriolis pull that spins global hurricanes, and the centrifugal push that allows astronauts to float in a delicate balance with gravity.
We watched the mathematics of gyroscopes tear airplane engines apart and saw how engineers harness that exact same stubborn rotational math to guide ships to true north without a magnet.
We saw how the simple bobbing of a child's toy top, the delicate dance of precession and nutation, scales up to become the cross-coupled torque nightmares of a multi-billion-dollar space station. We conceptually sliced airplane wings into lumped matrices to hunt for invisible weaknesses, and we tracked the mirror image ghost waves constantly racing across a plucked guitar string.
We saw how the spherical mathematics of a firework explosion dictate the sharp limits of sound, and we finally landed in the nonlinear chaos of a whirling steel shaft sprinting across the resonance minefield.
And we ended on the phase plane, watching the clean, predictable, closed circles of a pendulum swing stretch and distort as energy is added, until they finally shatter across the separatrix into open, tumbling chaos. And that phase plane is exactly where I want to leave you today.
It's a powerful thought.
Think deeply about the concept of the separatrix, that strict, absolutely invisible mathematical boundary that separates a world of stable, predictable swinging from a world of chaotic, over-the-top tumbling.
Right.
If physical objects, simple brass weights on a string, have these hidden absolute thresholds, where are the invisible separatrices in our own lives? Where are they in our local economies or our global supply chains or our societal systems? Are we casually adding energy to a system, adding stress, adding speed, adding friction, assuming that the circle will just get a little bit wider without realizing we're just a microscopic fraction of a degree away from a saddle point?
It's entirely possible.
Are we balancing at the top of the arc, ready to tip with the slightest breeze into irreversible chaos? It is something to think about the next time you find yourself swinging just a little too high. Thank you for joining us on this incredible deep dive into the hidden mathematics of motion. Keep exploring the invisible forces around you. Keep questioning the simple things, and we will catch you on the next one.